Welcome to today's lecture of Empirical Economics. Today I'm going to start right away, and then Mr. Trede is going to take over, and then we'll switch a little bit between ourselves in the process. Let me just share you my screen, and then we can directly go into the slides, which I hope that you can see right now. Last week, and in the week before, we introduced the main topic we are dealing with in this lecture. And in the previous week, we also talked in a bit more depth about R. And you have already seen the data set that will be joining us on the way to empirical economics for this semester, that we will encounter very often this term. That is the California school data set. And we have seen some scatter plots already of the data set, and we'll continue with working with the data set alongside the theory behind the simple linear regression model today. In the last week, we raised more or less the question, can we determine, or is there an association between the class size in the California school data set and the learning outcome? That would be the empirical question. Can we assess that? And then, of course, if we can determine that there is a relation between these two variables, an association between the variables, then, of course, it's an important policy question. What's the causal effect then of reducing the class size by a single or by one student or one child on the learning outcome? Because if we knew that, we could then optimize class sizes in order to get optimal results. So by setting the marginal cost of decreasing class size by one student equal to the marginal gain of the learning outcome. Now the question, or one question that obviously arises, is what is exactly the learning outcome? Because that is something that is, of course, might be either hard to measure or even difficult to define in the first place. So how would we measure a learning outcome? I think there are many dimensions to learning outcome. One might be, especially for younger children, is of course the parents' satisfaction. Are the parents satisfied with what their children learn and the way they learn it, the environment they learn it in? We can of course also look at the future earnings of children or the future welfare of children. That might be a very good indicator of our policies, how effectful our policies have been. But on the other hand, we're looking at future earnings. So possibly 15 or 20 years later, after we might have conducted an experiment based on increasing or decreasing class sizes. And then these 15, we don't want to wait 15, 20 years to get results, to get answers to the questions that we'd like to get answers right away to. So what we are very often looking at is at results of some comparative studies, for example, such as PISA, or at other standardized test results that we can apply directly after we have either an experiment or that we can observe at the same time as we observe, for example, the class size of students. And then we can compare class sizes and the outcomes of such standardized tests. And that's what we do in the California school data set. We have, the data set is taken from 1999, so it's already a bit older, but I think many things might be similar to the way they were back then, or at least back then these results held. We have all the 6-year and 8-year California school districts. It's 420 school districts. And what we obtain as data is the test score of the Stanford 9 achievement test, which is taken in the 5th grade. And we have a combination of the reading score and the math score. And that's something I told you about in the last week as well. And what we observe also is the student-teacher ratio. So the number of students in the district divided by the number of full-time equivalent teachers in the school district. That's the data that we are looking at today. And let's have a first look at the data with this table here. We have our two variables, STR for student-teacher ratio and test score for the result of the Stanford 9 achievement test. And as you can see, we have an average class size of roughly 20 students with a rather small standard deviation of about 2 students. And we see the 10 and 90% quantile and the median here reported in the table. And we see that class sizes are somewhere between 17 and 22. And the median is close to the mean in here is also almost 20. So in many cases, we have classes around a size of 20. Sometimes we go down as much as 16.5 or 17, but sometimes districts with average class size 16.5 or 17, but sometimes we have districts with little larger classes. On the other hand, test score has an average of 654 and a standard deviation of roughly 20, and the quantile ranges, and the 10% quantile is at 630, and the 90% quantile is at 680 roughly. So there is a bit more variation in the test score, as you can see here. Let's have a look at a graphical look at our data set. That's something we've already seen in the last week. We see this point of clouds here, this cloud of points, the scatter plot. And as you can see, maybe there might be a slightly negative dependence or association between the student-teacher ratio on our x-axis and the test score that you can see on the y-axis. So if you close an eye, get a bit back from your screen, then you might come to the conclusion that it seems that in this cloud, there should be, if we want to draw a line through this cloud, we should do it in a way that it has a slightly negative slope and some intercept roughly around maybe 700 or so. Now, what the policymaker is interested in, of course, is what's the quantitative effect of reducing said class size, so STR, by 1 unit, meaning 1 child per class, on our test score. So if we go, from 20 to 19, by how much does our test score, in this case, increase? So maybe from 600 up to 602 or something like that. And the relevant quantity, if we actually want to quantify that, is of course the slope of the line we would put through this cloud. And it is defined by the value we change our test score divided by the value, the delta of our test score, so the difference our test score has if we increase or decrease our class size. So just the normal formula to compute the slope of a line. Now the question, or one question that remains, is how can we best fit a curve or a line through this plot? So what would be the best line that we can put directly through this cloud, through this scatter plot, to be, so to speak, an optimal line? And Mr. Trede is going to take over to tell you how to do that. And you're still muted.
Okay, and can you see the pointer now?
No.
You can't.
No.
Okay, so I have to share my screen then entirely.
Yep.
Okay. Can you see it now?
Yes, perfect.
All right. Okay. By the way, if any of you has any question, just interrupt. You switch on your microphone and just interrupt, or if you prefer to use the chat, you are invited to do that. So just type your question into the chat. And since there are two of us, one of us is always following the chat and either answering directly inside the chat or just transferring the question to the other one. Okay, so we have already seen that the question at hand, the policy question we are interested in, is about the relationship between class sizes and test scores. And as Andreas has just explained, the interesting question is, can we say something about the test score if we know something about class sizes? And we start with what is called the population regression line, which at first sight is disappointingly simple because we just assume that there's a linear relationship between class sizes on the right-hand side, so STR's class size, and the test score on the left-hand side. And it's a linear relationship because we have coefficient beta naught and a coefficient beta 1. Beta naught is the intercept and beta 1 is the slope coefficient. Now, if we assume, and later on we will see that this is a standard assumption for good reasons, because it's usually quite a good assumption, or at least a good approximation to what we actually try to model. So if we assume that this linear relationship is true, then the coefficient we are really interested in is beta 1. This is the coefficient we want to know. So we are interested in the slope coefficient of the regression line. Or we should say here, the population regression line. And as you remember from, I don't know which class linear functions had been introduced in, but it's quite a long time ago. As you might remember, the slope coefficient is defined as the change on the left-hand side divided by the change on the right-hand side. So the slope coefficient is just the change in the test score given the change or divided by the change in the class size. So in other words, the slope coefficient tells us the change in the test score when the class size is increased by 1 unit. So if beta 1 is positive, that would mean that increasing the class sizes would improve the test results. That's not really plausible. What we expect is beta 1 to be negative. So if we increase the class size by 1, we would expect the test score to decrease by a certain level, and this certain level is beta 1. So beta 1 is the quantity we are really interested in. Okay, and this linear relationship between class sizes and test scores is not only applicable for this particular example, it's generally applicable. So it could be applied to any two variables you are interested in, not only in education economics, but in any settings, be it microeconomics or macroeconomics. So we introduce a more general notation here, and we introduce a general notation which goes along what you will find in any textbook internationally. So if you look at, say, a textbook from Brazil or from Japan or the US or anywhere, then you will find the same notation in all these textbooks. And the general notation is as follows. We have a linear relationship between a variable y on the left-hand side, then we have the coefficient, the intercept coefficient and the slope coefficient, beta naught and beta 1. We have a right-hand side variable x and some term ui, and I will now go through all these ingredients of the linear regression notation. So let's start with x. The x's are called regressor variable, but there are much more terms to talk about the x's. Different terms from regressor are exogenous variable, the independent variable, the explanatory variable, the right-hand side variable, or just right-hand side RHS, or the cofactor. In German, it's the same. So if you talk about the linear regression setting in German, dann würden Sie den Regressor X als Regressor bezeichnen, exogene Variable, unabhängige Variable, erklärende Variable, rechte Seite Variable sagt man nicht, oder Kofaktor. So all these terms are used interchangeably. I try to prefer the term regressor because that's very general, and since we are in a regression setting, it's a very telling term. So I think this is the term you should try to use most often. Apart from that, you will find the term exogenous variable quite often, but later on in the term, we will see that talking about exogenous variables on the right-hand side is not that good an idea. So I try to talk about regressor variables when I talk about the axis of the class sizes, for instance. And if you are more going into sociology or the more social sciences, apart from economics, then the term cofactor is used quite a lot. All right, so that's the right-hand side variable, the explanatory variable, the regressor. On the left-hand side, we have the yi, the test score, for instance, and the terms for the left-hand side variable are endogenous variable, dependent variable, or just the left-hand variable. Okay? And in German again, also it's the same. Wir sprechen von endogenen Variablen oder abhängigen Variablen auf der linken Seite. Then we have the intercept, beta naught. Sometimes it's denoted by alpha, but I think beta naught is more common. And we have the slope coefficient, which tells us how steep our curve is. So that's the slope coefficient, beta 1. And then we have this UI term, which is the last summoned here. And the UI term is usually called the error term or disturbance term. And usually in time series settings, we also talk about innovation terms. But I think the most common names are error term or just the disturbance. And these are the UI. And in German, it's Fehlerterm oder Störterm. Innovation sagt man eher nicht. And this error term contains everything that is not explained by the axis. So if you think back to the scatter plot Andreas has shown before, obviously the points are not on a linear line. They're not on a straight line. The points scatter around. It's really a cloud of points. So the error term captures everything which lets the yi deviate from the regression line. For instance, the UI may include omitted exogenous variables, omitted regressors, or it may include a measurement error for the endogenous variable. Omitted exogenous variables could be in the context of class sizes and test scores. Omitted exogenous variables could be the general environment in the school. Do the students have computers at hand to learn? Do they have good, new, innovative textbooks? So in some school districts, the school environment might be less good than in others. So that, of course, would be a factor that impacts the test scores. But since we do not include these data in our regression here, all these additional regressors or these additional impacts are just captured by the error term. And later on, we will see that that could be a serious problem if we are interested in causal effect measurement. So the error term is relevant because it captures the omitted exogenous variables and, of course, measurement errors. So for instance, in a certain school district, the test scores might be particularly bad for some reason, because the tests were conducted very early in the morning, much earlier than in the other school districts, and the students have been so tired that their test performance was much worse than in other districts, for instance. These measurement errors also go into the error term, into the disturbance term. So in short, the error term captures everything that impacts on y apart from the axis. So all the impacts on the test score which are different from class sizes. So all that is captured by the error term. That's the general notation. So we will jump to and fro between this general notation, if we talk about the regression model in general, and the particular example with the class sizes and the test scores. Okay, any questions so far? No. All right, so let's have a look again at the terminology. We have the regression line, and we assume here that it's actually downward sloping. So we have the intercept, beta naught, somewhere down here at class size 0. Then we have the slope coefficient beta 1, which is in this case slightly negative because it's downward sloping. We have 2 points, so x1 and y1. x1 would be slightly larger than 20, and y1 would be 680 something. And you can see that this point, this black point here, is not exactly on the regression line. So there is a positive error term here, and the positive error term is the red distance. That's U1. So this school district, for instance, school district 1, has a test performance which is larger than we would expect given the class size of slightly larger than 20. So we would expect the test performance which is around 660, but we observe a test performance which is about 680, so we have a positive error term here. If we go over to the second school district, which has smaller classes, so it's only about 17, but the test performance is only 630 or so, 620. So we have a negative error term here, and the U2 is the red distance I just showed here. Okay, so these are the error terms. The error terms are responsible for the deviations from the regression line. All right, so everything would be quite easy if we knew the true regression line, but we don't. Of course, nobody is telling us what the true regression line is. But we are interested in the true regression line. We want to know its slope, in particular its slope. So is beta 1 positive or negative? And if it's negative, how negative is it? How bad is it for a school district to have very large classes? So we are really, from a policy point of view, interested in beta 1. But since we do not know the true regression line, we do not have information about beta 1. So the question is, how can we estimate beta naught and in particular beta 1 from the data? And the answer is relatively simple and time-honored. It's a really time-honored concept. This idea is about more than 200 years old. So it's not modern rocket science. It's really very basic but very powerful technique. And the answer is the following, given in this formula down here. What we do to estimate the intercept and the slope coefficient is the following. We look at a sum. We look at the sum of squares of differences between the observed values yi for each school district, for instance, and the values that would be implied by a regression line, which is characterized by B naught, not beta naught, B naught and B1. Okay, so let's go again from inside to outside. First, we specify a regression line by its intercept B naught, which could be any value, and its slope coefficient B1, which could be any value. These values here are not the true values, beta naught and beta 1, but any values B naught and B1. So we specify a regression line, then we estimate for each unit, for instance, for each school district, the value which we would expect on the regression line given the class size is x. We compare that to the value that we actually observe, yi. We take the difference between these two values, that's the red distance from the previous slide. We square that red distance, And the effect of squaring it is that positive and negative deviations do not cancel anymore, because if you square positive quantity, it's still positive. But if you square a negative quantity, it's also positive. So all the deviations become positive by squaring them. And the second effect is that very large deviations get a higher impact, because squaring them makes them much larger than squaring small deviations. Okay? So we square those deviations, we add them up, and then we minimize this quantity we get. So this is, in a way, a measurement of how closely the regression line fits the cloud of points. And we then choose the intercept and the slope coefficient such that this deviation is minimized. And therefore, this is called the least squares estimation method. So least squares, the sum of the squared deviations is minimized. You have encountered that before in statistics 1, but it's always a good idea to repeat that. All right, so this is how we get the estimators for the intercept term and the slope coefficient. And these are called the OLS estimators. And in German, it's kleinste Quadrate Schätzer. Okay? So the OLS estimators minimize the sum of the squared differences of what we actually observe, the actual test scores, for instance, and the values that would be implied by the regression line. All right, and the standard notation in econometrics for such OLS estimators is the value with a little head on it. In German nennt man das Dach, beta 0 Dach, beta 1 Dach, and in English we talk about beta 0 head and beta 1 head. And it's quite important to distinguish between the true value, beta 0 and beta 1, and the estimated values, beta 0 head and beta 1 head. Okay? So these are different from each other because we do not know the true values, we only estimate them, and of course the estimates are different from the true values in general. Now, I just said that the OLS estimators have a certain property. They minimize the sum of the squared differences. And therefore, to find these estimators is quite simple for economists because minimizing and maximizing is what economists do all the time. So to find the minimum and to get the OLS estimators, we just apply the standard approach that is done in economics all the time. We take the derivatives of this quantity from the previous slide. We differentiate this quantity with respect to beta 0. We differentiate this quantity with respect to beta 1. So we take the two derivatives. We set both of them equal to 0. Then what we get is a system of equations, two equations and two unknown coefficients, beta 0 and beta 1. We can solve this system of equations, and if you really do that, you will realize that it's a linear system of equations, so it's very easy to solve that, and then you are done. Okay? We don't do that here step by step. So you've seen that before, and you can have a look at the textbook. We don't do that here because it's implemented in R and in any other computer package, and it's very easily done using a computer. So if you would really derive the OLS estimator step by step by following this approach, taking differentials, taking the derivatives, setting them equal to 0, solving that, and then you would get the following OLS estimators. The estimator for the slope coefficient is this one here. So you take the sum of a certain product. The product consists of deviations of the x's from their mean and the deviations of the y's from their mean, and you divide that by the sum of the squared deviations of the x's from their mean. So if you think back to statistics 1, you realize that the term in the numerator is almost identical to the covariance between x and y, and the term in the denominator is almost identical to the variance of x. And in fact, if you differentiate, if you take the ratio of the covariance between these two variables and divide that by the variance of the x's, then what you get is the estimator for beta 1. So this is the OLS estimator, and this is the result of really solving this minimization problem. Once we have estimated the slope coefficient beta 1 hat, it's very easy to derive the estimator beta 0 hat, because that is derived by or computed as the mean of the y values minus beta 1 hat times the mean of the x values. So first you compute beta 1 hat, and then using beta 1 hat you can compute beta 0 hat. These are the OLS estimators. And if you have fun doing these derivations, please just try to do that yourself. Try to derive these two estimators yourself. You can also have a look at the textbook. The derivations are given in there, and it's not too difficult, but we skip that here. Okay, so we now have a way to find estimators for the slope coefficient and the intercept term. And having data at hand, for instance, about the test scores in the school districts and the class sizes in the school districts, we can actually calculate beta 0 hat and beta 1 hat. And using these two estimators, we can then compute the predicted values of the endogenous variable. And these are called predictions in English and Prognosen in Deutsch, which is a bit misleading, because Prognosen usually refers to something in the future, while here it simply refers to certain points in our scatter plot. So Prognosen or forecast or predictions is not about future values here. That's a bit misleading, but you will quickly get used to this kind of terminology. So what are the predicted values? Well, the symbol for the predicted values is y hat, yi hat. And they are computed by evaluating the estimated regression line at xi. The estimated regression line is just beta 0 hat plus beta 1 hat times x. And if we substitute the x here or if we insert xi at this point, we get the value of the endogenous variable that we would expect at xi. Okay, so this is the value that we would expect given our estimation results. And we call this value yi hat. Of course, this is not the value that we actually observe. What we actually observe is yi. And of course, yi and yi hat need not be identical. And in general, they are not identical. So there's a difference between these two values, the value that we actually observe and the value that we would expect given our estimated regression line. And there's also a name and a symbol for this difference. The name is residual, or Residuum in Deutsch, and the symbol is u hat. So we compute the residuals by taking the difference between the observed values, the actually observed values, and the predicted values. And these differences are called residuals. Okay, so we have four quantities now that have little hats on top. The first one is the estimated intercept, beta 0 hat. The second one is the estimated slope coefficient, beta 1 hat. Then we have the predictions, yi hat for all the i's, and the residuals, ui hat for all I. And these are the estimators for the true quantities beta 0, beta 1, yi, and ui. Okay, so why do we use this approach? Why do we use ordinary least squares estimation? And there are actually a number of answers to that. One reason is that ordinary least squares is a very very natural generalization of the mean, of the average. For instance, if the regression line is forced to have an intercept of 0, so if in effect you just skip the exogenous variable, the regressor x, and just put its impact to 0, then what's left is only the intercept. And if you actually perform the OLS minimization, then what you will get as an OLS estimator for the intercept, beta naught head, is just the mean of the endogenous variable values. So y bar, just the average. So in a certain way, ordinary least squares regression is a generalization of this mean. So we compute the mean of the endogenous variable, but take into account that the exogenous variable, the regressor, might differ from observation to observation. So in this way, it's a quite natural generalization. The second reason why we use ordinary least have quite a number of desirable properties. For instance, they are unbiased, which means that the estimated value, we come back to that later on, but just as a precursor, the expectation of the estimator is equal to the true value, at least under certain conditions that we will talk about a lot during this term. What does that mean? That means that for the particular data we have, our estimator might actually deviate from the true value. But the approach that we have, this OLS approach, ensures that if we would repeat drawing data again and again and again, then on average, we would get the true value. So we would not systematically deviate from the true value. If the approach would systematically deviate from the true value, for instance, if we had an approach that would give us an estimator which tends to be larger than the true value on average, then that would not be a good estimation procedure, because we could improve our estimation by lowering the estimate a little bit. Okay? So OLS estimators have this nice property that they are unbiased under certain conditions. What's even better is they are efficient. So they have the smallest possible variance under certain conditions. What does that mean? Well, our estimator, we will see later on that our estimator is a random variable. So it might happen that the estimate we get is larger than the true value or smaller than the true value. But we want our estimation procedure to work in such a way that we would be that we are as close as possible to the true value. And luckily, OLS estimators have this property. So under certain conditions, there's no estimation procedure that would give better estimators. In other words, all the information there is in the data is squeezed out by OLS estimation. And we actually efficiently use all the information there is. It's theoretically not possible to find an estimator under these certain conditions that could squeeze out more information or better estimations than OLS estimators. And finally, OLS estimation is used by economists because it's used in all the empirical research, not only in economics, but also in sociology, actually in all empirical sciences. So you could call that the lingua franca of empirical research. So if you use OLS regression techniques, all your colleagues from economics and other sciences will quickly understand what you're doing and what the results actually mean. And that's quite useful. Okay, so let's apply OLS regression to our example data set. What does the estimated regression line for the California data set look like? And you can see here again the scatter plot that you have also already seen before. And I inserted here in red the estimated regression line. And as Andreas said, if you squint your eyes and go back from the screen a bit, you would also, well, actually put a line through this cloud of points, which is slightly downward sloping and which probably would be close to the optimal line you can see here. So this is the estimated regression line. We have an intercept, which is estimated as almost 700. So it's not here because the x-axis starts at 10, and to arrive at 700, you would have to go down all the way up to 0, which is probably here, and then you would be up at 700. Okay, and the slope coefficient is minus 2.3 roughly. So if we increase the class size by 1 student per teacher, the test score would go down, at least that's the interpretation here, by 2.3 points, which is not very much. So it's really just a slightly downward sloping line. So these are the estimates in this example. All right, let's also have a look at what the predicted values and the residuals are in this example data set. We just take out one district, Antelope, and we actually have data about this district. The data are 19.33 for the average class size and 657.8 for the average test score in this district. So these are the values that we really observe. We can also compute the predicted value per antelope using the regression line. So we use the estimated intercept, 698.9, minus the slope, 2.28, times the class size, the xi in this case. And we find that if we really calculate this, that the predicted value for this school district is 654.8. So this would be the value. Let's go back to the plot. What was the class size? 19.3. So for a class size of 19.3, roughly here, we would predict a value which is on the red line, roughly here, and that would be 654.8. This is the predicted value. Of course, the data in the school district deviate from this predicted value in general. And in this case, the deviation is 3, because what we actually observe is 657.8. What we predicted was 654.8. So the difference, the residual in this case is 3. So it's positive, which means that the actual test score in this district is a little bit larger than we would expect given the estimated regression line. All right, any questions so far? That's not the case. Then I hand over back to Andreas.
Okay, welcome back from my side. We have right now seen how to, technically at least, how to estimate the model, how to estimate the linear regression, and how to fit the perfect line through our clouds, through our scatter plot. What we haven't seen yet is how well does that line fit to our points? How well does that line actually explain the relationship between, in this case, student-teacher ratio, so class size, and the test score? We have only fitted the line, but we have not talked about how well does the line actually fit. Luckily, the data set or the data that we use cannot only be used to fit the line, but can also be used to tell us something about how well that fit has been. So can our exogenous variable class size, student-teacher ratio, explain a small part of the deviations that we see in test score, or can it explain a lot of the deviations we see in test score? In other words, are the points that we observe, are they very close to the regression line, or do they scatter wildly around that line? Let's have a short look back at our scatter plot. As we can see here, we have obviously not all the points are on the line, and not all the points are even close to the line. We have some points that are very close to our regression lines, but we have also some points like this point up here or that point down here that are very far away from our regression line. So we need some measures, some numbers that tell us, are these points here rather far away from our regression line? Do they scatter wild around the line, or are they actually pretty close? And two measures that we can use to assess that questions are, first, the R squared. That's one measure. And the second measure is that we are going to use now is the standard error of regression. So let's just start with our R squared. What we can see here is a decomposition in some terms of our observed value yi into the predicted value and our residual. Well, it's not really a decomposition because it's just a rewriting the definition of our residual as the observed value minus the predicted value. So we just rewrite that, and we can see that we have one part of our observed value that we would predict. So that is yi hat here. And we have another part of our observed value that we do not observe. So our residual. What we can do now is look at the variation. So the variance, but not standardized by the sample size, of our observed values. So the sum of the squared differences of our observed values from the mean value. And we can decompose that as well into the sum of the squared deviations of the predicted values from our average observation. And here it doesn't matter whether you put in y bar, so the average value of the observations, or y hat bar, the average values of our predictions, because they coincide, they are the same value. If you want to compute that, you can just find out by the very definition of the of OLS by, for example, seeing that the average of our residuals is always 0 due to the optimization routine. Plus, at the right-hand side here, the sum of the squared residuals. In here also we have we use the fact that the sum of the residuals is always 0, so the average of the residuals is also 0 as well. So implicitly we subtract the average of u hat, so u hat bar, from u hat here as well. So what you could write down here as well is ui hat minus u hat bar, but u hat bar is 0 anyways. So what we stick with is this formula. On the left-hand side, we have the total sum of squares. So the variation of our y variable of our test score. And on the right-hand side, we have the variation that we can explain with the regression line. So how much does the regression line vary? Plus the sum of the squared residuals, meaning the part of the variation that we cannot explain with our model, because UI incorporates all the parts of the model, all the variables that we do not incorporate in our model. And now we can just take these three variables and build up the R squared as the fraction of explained variation. So how much variation can we explain of the total variation? So ESS divided by TSS, or 1 minus the share of unexplained variation. As R squared is a fraction, and a fraction of numbers, as we go back one slide, that are only positive because we square in here, we only obtain positive values. So R squared has to be between 0 and 1 because we divide a positive number by a positive number that is larger than the numerator. So R squared measures the share of variation that we can explain with our model. R squared has no unit, it's just a fraction, just a share. And if r squared is very close to 0, then we cannot explain very much with our model. If r squared is very close to 1, then our model fits the data very well. Yes, as I said, if r squared is 0, then the explained variation is 0. So we cannot explain anything of the variation in our data with our model. And if r squared is 1, then we can explain everything of the variation of our dependent variable with our regression. Then all the points would be exactly on the regression line. And in case of a single regressor, r squared, that's practically equals the square of the correlation coefficient between x and y. So if you have a single regressor model, you want to compute the r square, but you forgot how to do that, and or how to make r doing that for you, then just compute the correlation, square it, and you have the r squared. The second measure of fit that we are looking into is the standard error of regression. It looks maybe a bit wild, this formula with the square root and the 1 over n minus 2 sum over ui hat squared. But if you have a closer look at it, you can see that we have here a sum of ui hat squared. I said before u hat bar, so the average residual is 0. So we could also write down this one in the fashion of a variance. So u hat minus u hat bar and then squared. And then we divide instead for the variance 1 over n or 1 over n minus 1, we divide by 1 over n minus 2. The reason for that is that we need, as you might reconsider from statistics 2, where we have the corrected variance by dividing through by n minus 1. So we have a bias correction here as well. We won't go into details of that. But this whole formula then resembles of a standard deviation formula, because we're taking here the square root of everything that has been computed so far. So this standard error of regression is nothing else than a formula for a standard deviation with slight modifications of our residuals. Then, of course, the standard error has the same unit as y. So if y is the test score and the test score is measured in points, then the standard error of regression is also measured in points. So if I have a standard error of 10, then this is for us an estimate of the standard deviation of our error, and says that a typical error or a typical residual is around the typical measurement as an error is around 10. Consider also that if that dividing by n minus 2 doesn't really make a big difference nowadays, especially if you're talking about larger data sets. If you have data in the many hundreds, many thousands, or even many 10,000 observations, it doesn't make a difference here at all whether I divide by n minus 1 or n. So just remember that. In our California schools data set, in the regression of student-teacher ratio and test score, we've seen, if we ran that in R and if we looked at the summer statistics of that regression, you will do that in the exercises later on, and tomorrow and on Wednesday, I think, you will obtain an R squared of 0.05 and a standard error of regression of 18.6. Now, is that large? Is that small? Does that explain much? Does it explain nothing at all? So let's have a look. The R squared, we said R squared is between 0 and 1. Must be between 0 and 1. Now this R squared value is 0.05, so it's very close to 0. So student-teacher ratio doesn't seem to explain that much. On the other hand, the standard error of regression was 18.6. And let's just compare that 18.6 to our table that we had seen here. The standard deviation of test score is in the same magnitude. So our model has an error in the same magnitude as the standard deviation of our test score. So again, that hints us to the fact that the model that we have estimated cannot explain very much of the relationship between class size and test score doesn't seem to be that strong. So does that mean that the student-teacher ratio, so class size, is unimportant? Not really. It only tells us that there are probably other variables that are also important, but because that we have already graphically seen, there is a slight negative dependence, but most likely there are other factors that should taken or that need to be taken into consideration as well. Up to now, we have used the regression model to describe the relationship between, in this case, student-teacher ratio and test score. We haven't done any statistical inference. We haven't done any confidence intervals for our parameters. We haven't done any hypothesis testing and so on. And additionally, the regression line that we have computed is based on a sample. Because we cannot observe the whole world, we can only observe small fractions of all the information that is in the world. And if we observed this whole data set, or if we had observed a different sample, so maybe we had done the tests at 10 in the morning, but at noon, then the sample would be slightly different, and we would have observed slightly different estimates. And now the questions are, can we quantify the uncertainty of our estimators? So can we quantify how certain we are that our estimator is in a certain range? How can we use beta 1 hat, our estimator, for hypothesis testings about the true parameter beta 1? How can we construct confidence intervals for this parameter beta 1? And to answer all these questions, we have to take one step back, because we need we need a set of assumptions that then again allow us to derive formulas to exactly quantify the uncertainty, do hypothesis testing, construct confidence intervals, and so on. In the case of the simple linear regression models, we have 3 assumptions. And all these 3 assumptions need to be fulfilled to have a valid model and to answer all the questions we've seen before in the slide before. They might look technically at first glance. Some of the assumptions are of rather technical nature. The third one, for example, but we try to show you the importance of these assumptions now in the subsequent lecture of today. The first assumption is that the conditional expectation of the error term given x has a certain value, and then for all of the possible values of x is always 0. What that precisely means, I'm going to show you in a minute. Let me just read out or tell you about the other 2 assumptions. The second one is that the pair of exogenous and endogenous variable, that these are IIDs, so identically and independently distributed. So they are from the same population, they don't depend on each other, so one person doesn't depend on the other person, and And the third assumption is that the expectation of x to the power of 4, so the 4th moment of x, and the expectation of u, or error term, to the power of 4, that these are finite. We'll come to that later on as well. First of all, let's have a look at our first OLS assumption. So the expectation of our error term given our regressor is equal to 0. What does that mean? And I think a good way to illustrate that is with a little R application. So let's go through that. We won't go through the code, but just through the plot. Let me just show you this plot here. And these points, I think, is this plot. I'm missing some lines of code, I'm sorry. Nevertheless, let's have a look at this plot. You can't see the whole cloud of points in here, unfortunately, but maybe I accidentally deleted a line of code there. You should see the whole line of the whole cloud that you have already seen a couple of slides ago. So I hope that you can just imagine these lines of code, these points. The red line here is the regression line that we just created from the data, that we just derived from the data. And what this assumption actually means is that, of course, the points deviate from that line. Of course, we don't have all the points exactly on the line, but there's no systematic deviation from that line based on class size here. So let's just pick these three levels of student-teacher ratio of class size. So 15, 20, and 25 as example values here. And what we need to be true is that our error term is distributed in such a way that its expectation is 0. So we don't have a systematic deviation of our points either to with increased test score or with decreased test score. And that must be true for all the values of class size. So for all the student-teacher ratio values. In other words, that means that the error term, U, is uncorrelated with our regressor. Now let's have a look what would happen if that was not the case. So that assumption was violated. Let me just run these lines of code. What we see in here is a violation of this assumption. Because in here, we have an error term that is correlated with student-teacher ratio. So for example, think of the error term. We said that the error term consists of all the variables that we exclude from our regression. So because we only include student-teacher ratio, so the quality of assistance that the parents can give to their children is missing from the regression. The number of computers in the school is missing from the regression. If these variables that are all included in the error term UI were in fact correlated with our student-teacher ratio, for example, in a way that in districts with small classes, so this 15 district here, that in these districts we have more computers, parents tend to be more able to help their children, so that in these districts, the actual test score is higher. We have a positive error here. Then we have a systematic deviation from 0, and the expectation of our error term, given the regressors, won't be 0 again. It won't be 0 then. On the other hand, in districts with small classes, with very large classes, we would expect then that we have fewer capabilities of less capable parents to teach their children. We might have fewer computers in class and so on, so that we have, on average, a negative error term here, or an expectation, a negative error term. So that the regression line that we estimate here is systematically different from what would be the true regression line if we incorporated all these factors into the regression. And this assumption, this first OLS assumption, let's go back now to the slides, is not a harmless assumption. It's, I think, the most important assumption that we need to make sure to be fulfilled. And if that assumption was uncritical, was unimportant, we would have a very short semester, a very easy semester, because we could stop after this week and after next week, maybe, if we include the multiple regression model. But this is actually the crucial assumption that founds what we are doing in this whole term here, because this we need to make sure, not from a technical point of view, because we cannot really test that very well, but from a point of view that we need to think about the design of our model. We need to think about the context of our model that we apply it in. We need to make sure somehow that this assumption is fulfilled in order to obtain valid regression results. So let's again come to the error term. In this case, the error term captures all the other factors, as I said. For example, the effort of parents, extra learning facilities in school, and so on. And this can be very well approximated with family income, maybe. In districts where the family income is very high, so we have wealthy districts, the out-of-school opportunities are better, reading support at home might be better, and at the same time, because schools might profit from the wealth of the parents by being assigned more tax from parents or any other way. This might be a good, this unexpected, these unobserved factors up here might in fact be correlated with the error term, which is a problem. But the assumption states, and the assumption implies, so this assumption, the expectation of u conditional on our regressor is 0, implies that family income, given any of the class size values, is constant, meaning family income and class size are uncorrelated, which is, at least from my point of view, a very hard assumption here. And if this assumption, if assumption 1 of our 3 assumptions doesn't hold, then we cannot really say anything valid with our regression models. We always need to make sure that this assumption holds. Let's come to the second assumption xi and yi, so the exogenous and the endogenous variable are IID. This one is usually fulfilled if we have a cross-sectional data set, and if all of our units have the same probability to be sampled, and if they are sampled independently. In general, this assumption is rather easily violated if we have time series data. So for example, if you think of an economic background, the interest rate today or the interest rate tomorrow obviously depends on the interest rate today. The interest rate doesn't vary wildly and completely random, but there is a correlation between the days or weeks or even months for the interest rate. So we would not have independently sampled interest rates if we observe the interest rate, for example, over a whole year. But in this case, this second assumption would be violated. But usually for our cross sections that we are looking into, this one is justified. Sometimes, if, for example, these tests would not be mandatory, but you could choose yourself whether or not you want to participate on the test, then you might have some selection problems, some self-selecting routines before even observing the test score. Then this assumption might be violated as well. And the third assumption, a rather more technical assumption that we need in order to get the errors of our regressors themselves, is that the fourth moment, or the expectation of x to the power of 4 and the expectation of u to the power of 4, that these are finite. This assumption is always satisfied if x and u have finite support. For example, in our student-teacher ratio example, the test score is between 600 and 800 something, or 700 and 800, I don't remember. This seems to have finite support because the test score cannot be, you can also either answer all the questions wrong, then you get 0 points, or you can answer all the questions correctly and then you get, I don't know how many points, but we obviously have a finite support here. That technically already justifies or satisfies this assumption. If we have reason to believe that our data is normally distributed, then this assumption is also satisfied. So assuming normal data, assuming data drawn from a normal distribution, if you can have any reason to do so from the context of the data, then this assumption is also satisfied. But problems might occur if we have heavy-tailed distributions. For example, in financial data, we often see that t-distributions, sometimes with very low degrees of freedom parameters, are a very good approximation of the data. And then we might not have finite fourth moments. In general, this assumption is also violated if we have large outliers. So in general, this assumption just states we don't want to have large outliers in our data set because large outliers heavily distort the results that we see from our regressions. So the first assumption is a really important assumption and a really hard to check assumption, hard to check that it holds. Assumptions 2 and 3 are a bit more technical nature and are sometimes much easier to assure that they hold. Okay, that's from me on measures of fit and the assumptions for OLS. So I'm going over to you, Mark.
All right, are there any questions concerning that part, the assumptions? Otherwise, I'd continue with the next few slides. Okay. All right, so I think that by far the most important take-home message here is that the estimator beta 1 hat and beta 0 hat are random variables. And that's the case because the data we get are randomly sampled. So if you look at the class size example, the California school data set, as Andreas already said, if you resampled these data, you would get slightly different outcomes. So for instance, if you would resample the data in this year, of course, you would get different results from 1999. But if you did that again, you would get slightly different results because on one day the students perform better than on another day. The average class sizes vary from month to month. So there's a lot of randomness in the data generating process. And that means that the data you use to calculate the estimators beta 1 hat and beta 0 hat are random. And if you use random data to compute a quantity, then of course this quantity is also random. That's the most important part. So you could argue here that if you did the sampling procedure again, then you would get a different result for beta 1 hat. Not widely different, but maybe only just slightly different. But the data would be different, and therefore, since beta 1 hat is calculated from the data, beta 1 hat would be different as well. So that's very important insight. The estimators are random variables because they're calculated from the sample, and the sample is generated randomly. Right. Now this has certain consequences because if beta 1 hat is a random variable, then we can ask all the questions we learned about in statistics too. So for instance, what is the expectation of beta 1 hat? That's an interesting question because it means what is the value that we would expect for beta 1 hat if we resampled again and again and again. And of course, if we did that again and again and again and get more and more data, we would like to get close to the true value. So we would like to have a procedure that is not systematically resulting in values which are larger than the true value or values which are smaller than the true value. We would like a procedure that on average in expectation results in the true value. So asking about the expectation of beta 1 hat is very important. Okay. if beta 1 hat is a random variable, then beta 1 hat has a variance. And the variance of beta 1 hat has an important interpretation. It's already been mentioned before. The variance tells us how precise our estimation is. If the variance is very small, that means that the value of the estimator is always close to the same true value. So it deviates just a little from the true value. While if the variance of beta 1 hat is very large, that would mean that the estimator would scatter around the true value in a very wide fashion. So in that case, we wouldn't put much confidence on our estimation. So the variance of beta 1 hat is also of interest. Also, further questions: what is the distribution of beta 1 hat? First in small samples, finite samples, and also in large samples. This distinction between finite samples and infinitely large samples might seem a bit artificial at the moment, because in reality, of course, we never have infinitely large samples, but it is really a practical distinction. A small sample is typically a sample size up to, say, I don't know, 50, 100 or so. And if we have really large number of observations, as we nowadays usually have, say 10,000 or so, then we would talk about large sample properties of our estimators. Okay, so let's answer these questions. What is the expectation? And we do not derive these results. I just state them here, and then we say a few words about that. So the estimator beta 1 hat, the random variable, is unbiased. That means the expected value of our estimator is equal to the true value. We've seen that result before, and it means that we are not systematically overestimating or underestimating the slope coefficient. So on average, averaged over all potential samples, our estimation procedure would yield the true value. Nice property, because it means that we already know that our estimation result is neither biased upwards nor downwards. Okay, so that's the expectation. After the expectation has been computed, we can continue to compute the variance of this random variable. And we have two different symbols for that. We can either write it this way or with the sigma squared symbol here, with a little sub-index for beta 1 hat for the random variable. So both mean exactly the same. It's just in notation convenience which one is used. And deriving this variance is tricky if the sample size is small, but if the sample size gets larger and larger, then certain terms drop out and can be neglected, and the terms that remain are the one given here. So if n is large, then the variance can be computed in this way. And we have a number of components here. For instance, if n gets larger and larger, we can see that this term converges to 0, which is nice because it means that the precision of our estimator gets higher and higher and higher. The variance gets smaller and smaller and smaller if the sample size increases, which means that if the sample size is infinitely large, our estimator has a variance of almost 0, which means we are very close to the true value. Okay, so that's also a nice property. We can also see that the variance of beta 1 hat also depends on the covariation, the variance of this product here, which is hard to interpret, but also on the squared variance of the axis. So the more variation we have in our regressor variable x, the larger the variance here, the better our estimation, the more precise our estimation for the slope coefficient. These are, this is visible from the formula for the variance here. The next question concerns the distribution. What kind of distribution does beta 1 hat have? And the answer is that the central limit theorem, which you might remember from statistics 1, which tells us that if you add up or if you average a large number of random quantities, the sum or the average will converge to normal distribution. And it does not depend on the original distribution of the single quantities. The central limit theorem tells us that if we add up just a large number of random quantities, it will result, the sum will have a normal distribution in the end. And this result can be used here. And again, we don't derive this result, we just state it here. We can derive, but we don't, that approximately beta 1 hat has a normal distribution. And this is very handy because if it has a normal distribution, we know the quantities. And if you think back again to statistics 2, where we talked about t-tests for the expectation of a random variable and confidence intervals for the expectation of a random variable, in statistics 2, we always use the normal distribution. We used quantiles of the normal distribution. For instance, the 97.5% quantile of the normal distribution was 1.96, this famous number that you will encounter again and again when you do t-tests or compute confidence intervals. So it is really a nice result that we know at least approximately the distribution of the slope coefficient, of the estimated slope coefficient. And it's approximately normal, and I can assure you that this approximation, if n is large enough, is really excellent. We already know the expectation of that normal distribution, because the expectation of beta 1 hat is beta 1. And we also know the variance of this normal distribution, because that's been cited here. Okay. So in effect, we know everything about the distribution of beta 1 hat. And that's quite an important result. All right. In a similar way, one could derive the approximate distribution of beta naught hat. And well, it's also a normal distribution, and it's also unbiased, and the variance can be estimated, can be computed from the data. So the variance can be derived here. Normally, we are not that much interested in the intercept term. We are much more interested in the slope coefficient, because it tells us how much the endogenous variable will change on average if we fiddle around with the exogenous variable. All right, so these distribution results about the estimators beta naught hat and beta 1 hat, they hold under the OLS assumptions that Andreas had introduced before. Okay, so if the OLS assumptions 1, 2, and 3 do hold, then we can derive the distributional properties of our OLS estimators. And of course, if the assumptions are violated, then the distributional properties will be different. Okay, one important remark here, it is not necessary that the error terms are normally distributed to arrive at the approximate normal distribution for our coefficients. So the normal distribution, the normality, the Gaussianity for the OLS estimators does not hinge on the normality of the error terms. You will find this result, the statement sometimes, but it's not the case. The normality results from the central limit theorem. So it does hold even if the error terms are not normally distributed. Even then, our estimators will have a normal distribution. So in a way, it pops out from nowhere, and that's quite a deep result and quite interesting result, I think. All right, so if beta 1 hat has an approximately normal distribution with expectation beta 1 and this variance here, then we can do standardization. And we've also talked about standardizations in statistics too. Standardizing a random variable means that we first subtract its expectation, and then we divide this difference by the standard deviation. The standard deviation is the square root of the variance. And we can do that here because we know that beta 1 hat, at least approximately, has a normal distribution. We know the expectation and we know the variance. So we can standardize this random variable. We take beta 1 hat, we subtract the expectation, we divide the entire thing by the square root of the variance. Please note there's no square here, but there's a square here. So this is the variance. This is the standard deviation. And standardizing means that we get a new random variable, which in this case is this fraction here, with expectation 0 and variance or standard deviation 1. So by standardizing this normal distribution, we get a standard normal distribution, at least approximately. Okay? And this result will be very convenient later on and very important later on. And we can do the same thing for the intercept. Okay? So again, we can subtract the expectation, divide by the standard deviation, and what we would get is an approximate standard normal distribution. This is how far we wanted to get today. Are there any questions? So please use the chat or just ask. We can stop the recording, I think. So if you feel